So this is ELC 111. And what we're going to do in this presentation is look at putting all these parts together to build an EEG system. So coming into our EEG system, we've got a series of leads. Let's just refer to those as L1, L2, L3, L4, L5, L6, L7, and L8. And these leads are going to go into a component. And let's make that component about that big. Finish all these up here ever so nicely. And this component is a multiplexer. Can you say multiplexer? Very good. Now we can also think about this multiplexer as being a data selector. And we'll talk about this in a few minutes. But as you see, this multiplexer has 8 inputs, and it's going to have 1 output. The output of the multiplexer is going to go into a filter circuit. And for our filter circuit, I'm simply going to use a low-pass filter. I looked at a lot of different block diagrams or EEG systems on the internet, and I've seen some descriptions that use a combination of high-pass filters and low-pass filters and band-pass filters. I've seen some that use low-pass filters and band-pass filters. My thought is that all we need here is a low-pass filter, since we're looking only at signals that range anywhere from about 4 hertz up to about 60 hertz. I don't understand why some block diagrams showed using a high-pass filter, because that would attenuate all these low-frequency signals. And I think I'm pretty well spot on that again, looking at the low-pass filter will pass everything from 0 hertz or DC up to around 50 or 60 hertz. We don't want to attenuate our gamma signals, but we do need to suppress the 60 hertz noise that we see present coming into our system. Now, the output from the low pass filter is going to go into an amplifier, and we'll just draw our traditional symbol for an amplifier here. But in most cases, this is going to be what we call a programmable gain amplifier. And I'll show the connections here in a minute. I'll just draw it A here for our amplifier. We'll talk about the operation of this programmable gain amplifier and why it's important here. Now, the output of our amplifier is going to go into a circuit here. I'll write SH here, and this is our sample and hold circuit. And again, we'll talk about this in greater detail in a few moments. As the name implies, the purpose of this block is to sample the analog input voltage and hold it for a particular period of time. And the output of the sample and hold circuit is going to go into our analog to digital converter. And we've talked about the analog to digital converter, how it takes an analog voltage and converts it to a binary value so that we can send it then into our microprocessor or microcontroller. If I got enough room to write all this in here. Microprocessor, C-E-S-S-O-R, or microcontroller. There we go. And again, the microprocessor or microcontroller is simply the device that we program, and it sends signals out to everybody else to control the operation of the system. Now, our microprocessor has got to communicate back and forth with some memory, and memory is where we're going to store the data that we get from the analog to digital converter, as well as store the program that that the microprocessor needs to operate, and saves the information that's going to be sent over here, of course, to our display unit. And so we're going to put one more block over here, and this is going to be our display, or as we call it here, our strip chart recorder. There we go. Okie doke. So as we talked about in the analog to digital converter presentation, we're going to have to send a signal to the analog to digital converter that was labeled then to be our start conversion signal. So the microprocessor has to tell the analog to digital converter when to actually perform a conversion. The microprocessor, microcontroller, is also going to have to send a signal to the sample and hold circuit. And well, we won't have to put a label on that. I guess we can to tell it when to sample, similar to the start conversion signal. And our microprocessor or microcontroller is also going to have to send some information, and I'm going to draw this as a bus because this is going to be more than one wire here. There we go. That's nicely done. So we're going to send some digital information from the microcontroller to this programmable gain amplifier to control the gain of the system. So as part of the calibration process, the microprocessor, we really want to have the ADC be able to reach its entire limit. For example, if it's an 8-bit system, we want to use all 8 bits to store our digital values. Generally speaking, we want the output of this programmable gain amplifier to range anywhere from 0 volts to 5 volts. So depending on the voltages that come in from the leads, we can change the gain of the amplifier so that we're reaching our limits here of the maximum voltage, 0 to 5 volts. So the microprocessor sends out digital information to change the gain of this amplifier. And then lastly, we're going to need some information to go over here to the data selector, to the multiplexer. And again, I'm going to just draw this as a bus, not knowing exactly. Well, I do know how many wires I've got to have. Hang on just a second. So we know that this is actually going to only be 3 bits of information on this bus. Going into the multiplexer, we only need 3 wires, and that is to select one of 8 inputs. So we know that this is going to be 3 bits. Typically they're labeled C, B, and A. This will be my output O right here. So this is my take on the on a block diagram for our EEG system. Now, the multiplexer, I've got room to write down here. Multiplexer, we think of this, or my memory aid has always been that we think this is many to one. I remember that the first letter of multiplexer is an M for many to one. And again, we call this a data selector. And the way this multiplexer works is that if we look at our 3-bit input, C, B, A, and then an output, O, C is the most significant bit, B, A is the least significant bit. We've got 8 inputs, and these 8 inputs are going to be labeled I0, I1, I2, I3, I4, I5, I6, and I7. I barely fit them in there. So if the CBA inputs are 0, 0, 0, then input 0 is passed to the output. So it's like there's an electronic switch inside of here. If the CBA inputs are 0, 0, 0, then I0, which is lead 1, is passed through. This input is passed through to the output. And if the CBA inputs are 0, 0, 1, then input I1 is going to be passed through to the output. And you see that why they label these input 0, input 1 is this is equal to 0. It's the binary value of 0. This is the binary value of 1. So for a CBA input of 0, 1, 1, 0, which input would then be passed to the output? Well, it would be I2, and 0, 1, 1 would be I3, so on and so forth, up to 1, 1, 1 would be I7. So the microprocessor, what it's going to do is first put the 0, 0, 0 on the CBA lines, and of course the information, the voltage from lead 1 will be passed to the low pass filter. We amplify it, we sample and hold, we convert it to a digital number, we store that number in memory, and then the microprocessor, of course, would output a 0, 0, 1. The voltage from lead, I said, yeah, from lead 2. So this is lead 1, this is lead 2, this is lead 3, this is lead 4, all the way up to lead number 8. So again, the microprocessor will first get information from lead 1, then it'll get information from lead 2, lead 3, lead 4, all the way up to lead 8. And then of course it starts all over again at lead 1. And that way we don't need 8 separate low pass filters. We don't need 8 amplifiers. We don't need 8 sample and hold circuits. We don't need 8 analog to digital converters. We read from these one at a time, as shown. So the next block, of course, is the low pass filter. We've talked about filters fairly extensively in a previous weekly unit. And again, with my low pass filter, I want to have a cutoff frequency that could either be 50 or 60 hertz, depending upon, well, I'm not sure what it depends on, but I'll say 60 hertz. Again, if we have our cutoff frequency at 60 hertz, My thought is that we're prone to get a lot of 60 hertz energy into the system. I guess it's a question of where we want to limit the gamma wave information, or if we do want to limit it, or how much we want to limit it. So then we look at the programmable gain amplifier, and again we talked about amplifiers in the presentation. You know, the purpose of this is to amplify the input signal, but also to reject any common noise signal, any noise that's present coming in from the leads and managing to get through the filter block. So for my programmable gain system, for example, we could have 3 inputs. Let me make a note here. Programmable gain. So for example, again, we could think about this programmable gain system as having 3 bits, which would give us 8 different gain values to put in place for the amplifier. So if we think about, again, these 3 inputs as C, B, A, and then we look at what the voltage gain would be, for instance, that for a 0, 0, 0, we could have a gain of, let's just pick a number. Let me see my calculator. A gain of 41.7. And if this was a CBA input of 001, we could then change this gain to a different value. So let's just say 50. We'll just pick some numbers here. And 010, the gain could be 62. 011, we'll pick a different gain of 70. So depending upon what our input voltages are, again, from what I've read, the voltages coming from the leads can be anywhere from, I think it was 50 millivolts. Let me see what I had here. I don't remember where I wrote that down, but we'll say 50 millivolts ranging up to 120 millivolts. We could change the gain of the system so that we could amplify this, the lead voltages appropriately to give me a maximum output voltage of this block right here. So my output voltage V out max would be equal to 5 volts. So again, and this would be part of our, I'll say our calibration or operation procedure. The microprocessor would be sending out information here to set the gain of that block as appropriate, to give us the optimal or maximum output voltage of the amplifier. Excuse me. Now let me go to a new sheet here to kind of look at the sample and hold circuit. We haven't talked about this yet. But my sample and hold, so here we're looking at the output of my programmable gain amplifier. And then the sample and hold circuit would consist of, first and foremost, of a transistor. And this is my input point to the transistor where I'm going to send the information, which will just simply be a pulse. And this, of course, is from the microprocessor. Now, the output of this transistor goes to nothing more than a simple old everyday capacitor. And then this goes into my ADC. So my sample and hold circuit is simply this right here. There we go. So that's my sample and hold circuit. Now, with a transistor, when we provide a high voltage to the base, the transistor acts like a closed switch. So the output of this amplifier is going to allow current to flow over here and charge up this capacitor positive to negative as shown. Now, when this pulse from the microprocessor goes back low, now this transistor acts like an open switch. This current stops, and whatever voltage we have on the capacitor will stay there. In other words, it holds that voltage until we sample it again. So this signal right here is my sample, of course, sample circuit. So when this signal from the microprocessor goes from a logic 0 to a logic 1, then we turn this transistor on. Again, it acts like a switch, allows current to flow and charge the capacitor up. And then when this pulse from the microprocessor goes back low again, then it holds that voltage on the capacitor. So we have a consistent voltage, if you will, to go to the ADC. Now, if I look at these signals, and let's have a signal coming in here. This is going to be my start conversion signal. So what will have to happen from the microprocessor is that we're going to send this sample signal so that we can charge the capacitor up and hold that voltage. And then we're going to send the start conversion signal at some point afterwards. So at this point, that voltage will be stable on the capacitor. And the reason we do that is that if I didn't have this sample and hold, and the output right here is a noisy signal, as we saw in our amplifier lab, that even though we were filtering out this information with our low pass filter, we're still going to get some electrical noise on this analog voltage. And if I convert during this entire period from here to here, then we've got this changing voltage coming into the A to D converter, which I don't want to say it'll confuse him, but we really want a nice constant voltage here for the ADC. So what's going to happen is that if we look at this signal, and I'll sketch this out right here. So this is what's coming into my sample and hold circuit. If I sample it right here, so this is my sample signal, and we it's always better with sound effects. Then it's this voltage right here that's going to be held on the capacitor. So this, regardless of what's happening at the input, we're going to hold this voltage on the capacitor. And we've got, again, a nice constant voltage to be applied to the ADC. So we don't have to worry about any noise issues coming into the analog to digital converter. So again, after we've got this constant voltage out of the sample and hold circuit, we provide a start conversion signal to the analog to digital converter. It finds this 8-bit number, sends it to the microprocessor. Now the microprocessor knows which lead it's reading from. He knows whether he's sent out a 000, a 001, a 010, etc. on these 3 wires. So he knows what lead that digital information corresponds to. So in memory, he's got one area of memory where he's saving lead 1 information, another area in memory lead 2. And again, that's all part of the programming of this, that he's able to keep track of where in memory he stores that last digital value. And of course, he can take those values from memory and send them over to the display unit, to the strip chart recorder, and provide us graphical information. Again, I ran out of room for my block diagram, but of course this could go to a wireless telemetry system. It could go to whatever mechanism we're going to use to transmit this information from one place to another. So we've got a lot of different options of what we're going to do with this information when we get done. So this is my take on the entire EEG system, looking at it with respect to a block diagram, where again, with the exception of what we looked at with the sample and hold circuit, showing the transistor and the capacitor, we don't really think of this in terms of schematic symbols of resistors and capacitors and transistors and such. We just sort of take this low pass filter block as this block. Don't really care about what's inside of here, the capacitors, the resistors. We don't worry about the transistors that make up the amplifier. Again, we only looked at the sample and hold because that was somewhat new information. But this is sort of how all this stuff works together to make a functioning system that we can use to gather and store and display EEG waveforms.